Introduction and positioning in the OC model. You have already explored layers 1 and 2 of the OC model. You know that layer 1, physical, handles signals and transmission media, and that layer 2, data link, manages the framing of data, error detection, and communication between two directly connected devices using MAC addresses. Now it is time to go one step higher and understand what happens when data needs to travel beyond a single local network. This is precisely what layer 3, the network layer, is designed to handle. Layer 3 is the layer responsible for routing data between different networks. It introduces two fundamental concepts that you must master: IP addressing, Internet Protocol addressing, and routing. These two concepts are inseparable and form the backbone of how the entire Internet, and any private network of networks, functions. What is Layer 3 and what problem does it solve? Imagine you are on your computer at home. You want to visit a website hosted on a server located in another country. Your computer is on your local home network. The server is on a completely different network, potentially thousands of kilometers away. Layer 2 alone cannot solve this problem. MAC addresses only work within the same local network segment. Once you cross a network boundary, you need a different addressing system, one that works globally. That is the job of Layer 3. Layer 3 solves the problem of internetwork communication. It defines how data packets are addressed with globally unique logical addresses, and how those packets are forwarded from one network to another until they reach their final destination. The primary protocol operating at Layer 3 is the Internet Protocol, commonly known as IP. It exists in two major versions: Internet Protocol version 4, IPv4, and Internet Protocol version 6, IPv6. IPv4 remains dominant in most teaching and practical contexts, and we will focus on it here, though IPv6 will be mentioned where relevant. IP addresses, the logical identity of a device. An IP address is a logical address assigned to a network interface. Unlike MAC addresses, which are burned into the hardware and identify a physical device, an IP address is configurable and identifies a device's location within a network topology. An IPv4 address is a 32-bit number, written as 4 decimal values separated by dots. Each decimal value represents 8 bits, called an octet. For example, 192.168.1.10. This address has 4 octets: 192, 168, 1, and 10. Each octet can range from 0 to 255, giving a total theoretical address space of approximately 4.3 billion unique addresses. An IPv6 address is a 128-bit number, written in hexadecimal notation separated by colons, for example, 2, 0, 0, 1, 0, D, B, 8, 8, 5, A, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, D, A, 2, E, 0, 3, 7, 0, 7, 3, 3, 4. IPv6 was designed to solve the exhaustion of IPv4 addresses and provides an astronomically larger address space. Network addresses and subnet masks. An IP address alone is not enough to understand the structure of a network. You also need the subnet mask, which tells you which part of the IP address identifies the network and which part identifies the specific device, called the host, within that network. For example, consider the address 192.168.1.10 with a subnet mask of 255.255.0. The first 3 octets, 192.168.1, identify the network, and the last octet, 10, identifies the specific host on that network. Any device with an address in the range 192.168.1.1 to 192.168.1.254 is considered to be on the same local network, or subnet. The subnet mask can also be written in a shorthand notation called CIDR, classless interdomain routing notation, where the number after the slash indicates how many bits are used for the network portion. So 192.168.1.10 out of 24 means the first 24 bits identify the network, equivalent to the mask 255.255.255.0. Two special addresses exist within any subnet. The network address is the first address in the range, for example, 192.168.1.0. It identifies the network itself and cannot be assigned to a device. The broadcast address is the last address in the range, for example, 192.168.1.255. It is used to send a message to all devices on the network simultaneously. Understanding subnets is critical in cybersecurity because network segmentation, dividing a large network into smaller subnets, is a key defense strategy. It limits the spread of attacks by isolating different parts of an infrastructure. Public and private IP addresses. Not all IP addresses are used on the public internet. Certain ranges are reserved for private use, meaning they can only be used within internal networks and are not routable on the internet. The three private IPv4 address ranges are 10.0.0.0 to 10.255.255.255, often written as 10.0.0.0 out of 8, 172.16.0.0 to 172.31.255.255, often written as 172.16.0.0 out of 12, 192.168.0.0 to 192.168.255.255, often written as 192.168.0.0 out of 16. When a device with a private address needs to communicate with the internet, a mechanism called Network Address Translation (NAT) is used. NAT, typically performed by a router or firewall, translates the private address into a public address before the packet leaves the internal network. This is why multiple devices in a home or company can share a single public IP address. From a cybersecurity perspective, recognizing private versus public addresses is essential during network reconnaissance. Tools like Nmap are used to discover active hosts and their addresses, and understanding this distinction helps you immediately know whether a target is internet-facing or internal. The IP packet, structure and key fields. At Layer 3, data is encapsulated into a structure called an IP packet, or IP datagram. Just as Layer 2 wraps data into an Ethernet frame with a header containing MAC addresses, Layer 3 wraps data into an IP packet with a header containing IP addresses and other routing information. The key fields of an IPv4 packet header include: version, indicates whether this is an IPv4 or IPv6 packet, value 4 for IPv4. Internet header length, specifies the size of the IP header itself. Total length, the total size of the packet, header plus data, in bytes. Time to live, TTL, a counter that decreases by 1 each time the packet passes through a router. When TTL reaches 0, the packet is discarded. This prevents packets from looping endlessly in the network. A typical starting TTL value is 64 or 128. Protocol, indicates which upper layer protocol is carried in the payload. For example, value 6 means the payload contains a TCP segment, value 17 means UDP. Source IP address, the IP address of the sender. Destination IP address, the IP address of the intended recipient. These fields are directly relevant to cybersecurity. For instance, attackers can craft packets with fake source IP addresses, a technique known as IP spoofing. The TTL field is exploited by tools like Traceroute to map network paths. Analyzing raw packets using a tool like Wireshark allows security professionals to read these fields directly. Routers, the key devices of Layer 3. The central device of Layer 3 is the router. While switches operate at Layer 2 and forward frames based on MAC addresses within a local network, routers operate at Layer 3 and forward packets based on IP addresses between different networks. A router receives an incoming packet, reads the destination IP address in the header, consults its routing table, and decides where to send the packet next. This process is called routing or packet forwarding. A routing table is a database maintained by the router that maps destination network addresses to the next hop, the next router or device to which the packet should be sent. The router does not necessarily know the full path to the final destination. It only needs to know the next step. Each router along the path makes its own forwarding decision. This distributed decision-making is one of the reasons the internet is robust against failures. For example, suppose your computer at 192.168.1.10 wants to send a packet to a web server at 93.184.216.34. Your computer sends the packet to your home router, the default gateway. Your router looks at the destination address, determines it is not on the local network, and forwards the packet to your internet service provider's router. That router forwards it further, and so on, until the packet reaches the destination server. Each step is called a hop. Default gateway. When a device wants to communicate with a destination outside its own subnet, it sends the packet to a special address called the default gateway. The default gateway is the IP address of the local router interface, the exit point of the local network. For example, on a home network with the subnet 192.168.1.0 out of 24, the default gateway is typically 192.168.1.1, the router's local interface. Every device on the network is configured to send all non-local traffic to this address. In a cybersecurity context, identifying the default gateway is one of the first steps in network reconnaissance. It reveals the presence of a routing device, which may also act as a firewall or provide other network services. Static and dynamic routing. Routers can learn routes in two ways, statically or dynamically. With static routing, a network administrator manually enters each route into the routing table. This is simple and predictable, but it does not adapt to network changes automatically. It is commonly used in small stable networks or for specific routes that must always take the same path. With dynamic routing, routers automatically exchange routing information with neighboring routers using routing protocols. These protocols allow routers to discover new paths, detect failures, and update their routing tables in real time. Common routing protocols include RIP, Routing Information Protocol, OSPF, Open Shortest Path First, and BGP, Border Gateway Protocol. BGP is the protocol that runs the global internet, connecting thousands of autonomous systems, large networks managed by internet service providers and organizations. From a security standpoint, dynamic routing protocols can themselves be attacked. For example, a rogue router can inject false routing information to redirect traffic, a technique called route poisoning or BGP hijacking. Understanding how routing works is therefore a prerequisite for understanding many network-level attacks. ICMP, the diagnostic protocol at Layer 3. Alongside IP, another important Layer 3 protocol is the Internet Control Message Protocol, ICMP. ICMP is used to send error messages and operational information about the network. It is not used to carry user data but rather to communicate information about network conditions. The most well-known use of ICMP is the ping utility. When you run the command ping 8.8.8.8, your computer sends an ICMP echo request to the target address. If the target is reachable, it replies with an ICMP echo reply. This tells you the host is alive and gives you the round-trip time in milliseconds. Another important use is traceroute, which uses either ICMP or UDP packets with increasing TTL values to discover the path a packet takes through the network. Each router that drops a packet, because TTL reached 0, sends back an ICMP time exceeded message, revealing its address. In cybersecurity and penetration testing, ICMP is frequently used during the reconnaissance phase to discover active hosts on a network. Nmap uses ICMP ping sweeps to quickly identify which IP addresses respond. However, many firewalls block ICMP, so the absence of a response does not always mean the host is down. Fragmentation at Layer 3. Different physical networks have different limits on the size of the data they can carry in a single frame. This limit is called the Maximum Transmission Unit, MTU. Ethernet, for example, has a default MTU of 1,500 bytes. If an IP packet is larger than the MTU of the network it needs to traverse, the router will fragment it, that is, break it into smaller pieces, each with its own IP header. The destination device reassembles the fragments back into the original packet. Fragmentation is relevant to cybersecurity because it has historically been exploited in attacks. Tiny fragment attacks and overlapping fragment attacks were used to bypass early firewalls and intrusion detection systems by hiding malicious payloads across multiple fragments. Modern security equipment is designed to handle these scenarios, but understanding fragmentation remains important. Encapsulation at Layer 3 in the OC stack. As you learned with Layer 2, encapsulation is the process by which each layer adds its own header, and sometimes trailer, to the data passed down from the layer above. At Layer 3, the transport layer data, a TCP segment or UDP datagram, for example, is received from Layer 4 and encapsulated into an IP packet by adding an IP header. This IP packet is then passed down to Layer 2, which encapsulates it into an Ethernet frame by adding a MAC header and trailer. Finally, Layer 1 transmits the resulting bits over the physical medium. At each hop, each router, the Layer 2 frame is stripped off, decapsulated, the IP packet is read, the destination IP is consulted against the routing table, and then a new Layer 2 frame is built for the next segment of the journey. The IP header, however, remains largely unchanged throughout the journey, except for the TTL decrement. This is a crucial distinction. MAC addresses change at each hop, but IP addresses stay constant from source to destination. Practical cybersecurity implications. Understanding Layer 3 is not just theoretical, it has direct and immediate applications in cybersecurity. IP spoofing. Attackers can forge the source IP address in a packet header to impersonate another host or to hide their identity. This is used in distributed denial of service, DDoS, amplification attacks, where the attacker sends requests with the victim's IP as the source address, causing massive responses to be directed at the victim. Network reconnaissance with Nmap. Nmap sends specially crafted IP packets to discover hosts, open ports, running services, and operating systems. Understanding IP and ICMP is essential to interpreting Nmap results correctly. Packet analysis with Wireshark. Using Wireshark, you can capture IP packets and inspect every field of the header, source and destination, IP, TTL, protocol, fragmentation flags. This is used both for troubleshooting and for detecting suspicious traffic. Firewall rules operate at Layer 3 and Layer 4. Firewalls filter traffic based on source and destination IP addresses, Layer 3, and port numbers, Layer 4. Understanding Layer 3 is prerequisite to configuring and bypassing firewall rules. Network segmentation as a defense. Dividing a network into subnets using routers or firewalls limits lateral movement by attackers. If an attacker compromises one subnet, they cannot directly reach another subnet without passing through a router, which can be monitored and filtered. Summary of key concepts. Layer 3, the network layer, is responsible for logical addressing and routing of packets between different networks. The core protocol is IP, Internet Protocol, which provides globally unique logical addresses. IPv4 uses 32-bit addresses written in 4 octets, for example, 192.168.1.10, while IPv6 uses 128-bit hexadecimal addresses. Subnet masks and CIDR notation define which part of an address identifies the network versus the host. Routers are the key Layer 3 devices. They read destination IP addresses and forward packets hop by hop toward their destination using routing tables. The default gateway is the local router a device sends non-local traffic to. The time to live field prevents infinite loops. ICMP provides diagnostic functions such as ping and traceroute. Encapsulation at Layer 3 wraps Layer 4 data into IP packets. MAC addresses change at each hop. IP addresses remain constant end-to-end. All of this knowledge is directly applicable to network reconnaissance, packet analysis, attack understanding, and secure network design in a cybersecurity and DevSecOps context.